Hi, I'm Mark Wilson, the engineering heretic. Today we're just going to look at a theory thing here. We're going to look at dividing heads, and in particular setting up a milling machine, a horizontal mill or even a vertical mill for that matter, for helical milling. And I do actually have a manual for a Mecha universal dividing head. This is a universal dividing head, not a plain dividing head. There is a difference. A universal dividing head has a take-off shaft here and also another separate take-off shaft on the back here as well, but we'll ignore that one for the moment. That's for another thing as well. But we're talking about this input shaft here and how we connect this up to a milling machine to do helical milling. This was back in the day in about 1976 during my apprenticeship. This was the most complicated thing you could do on a milling machine. It was called complex milling, and there is still even today a unit in our metals package for helical milling, or I think it's called it's using an omniversal mill or a universal milling machine, and this of course is a universal dividing head we're talking about here. And of course we had to do a project in that to prove our worth as far as being able to use a milling machine in that particular regard. This particular dividing head here, I don't have this one. I do have another one, which is it's from a machine called the Nova. It has very similar to this one here. We have the regular quadrant plate and plate for a Brown and Sharp system. The only machine that's not Brown and Sharp is the Cincinnati one, and that's for indexing. So we'll talk about indexing in another thing here, but we're talking about helical milling here. What is helical milling? Helical milling is the spiral flute you see on drills, milling cutters, end mills, helical gears where the teeth, rather than straight cut, they're actually around a helix. Okay, and we're talking about cutting that particular helix on a milling machine. Now in this particular book, we would like to, first of all, we're going to have a quick browse through this book here, where we're looking at, this is the universal dividing head itself. There's all its components. It does have another, a higher version of this, but it's the same one as that, except that it is a raised up version for getting larger work pieces in. Now, there's a number of things about this dividing head, but if you're familiar with them, you'll know what I'm talking about. Now we want to look at working out something here. Let's give a particular scenario, and we will endeavour to come up with the change gears to suit this. First of all, let's say we have a 40 mil diameter thing we want to cut a helix on. We're going to do I want a right handle helix here, so the helix is going to go around here like that, going around like that on this round shaft here. And we're going to cut this either a groove or something like that. Going around here, that's a right-handed helix running around that way. This here is 40 mil diameter. 40 diameter. And the angle on the helix here is square to the axis here, which is square this way here. We're going to make this 10 degrees. Something pretty simple. 10 degrees. Okay? So that's what we want to work out the ratios for this. Now, there is a few ways you can do mathematically work out what that. Now we're going to talk about something here called the lead of the work. There's also the lead of the machine as well. Now the natural lead of a milling machine depends on what the lead screw is. So if you have a milling machine that has a 5mm lead screw on the X table here, there's the table, okay, and the screw here is a 5mm lead. If you geared a dividing head up 1 to 1, of course, if you rotated the handle as if it was engaged 1 to 1 ratio into the dividing head, and cranked that around 40 times, 45s, I believe, comes up to 200 millimeters. I think that's right, 45s, or 1 to 1 for 40 turns, which will turn this particular dividing head round one for the main spindle round one full revolution. And that is what's called the natural lead of the machine. It's called the lead of the machine here is worked out. That's the lead of the machine. The natural lead of the machine. Now, of course, we have also the lead of the work. Now, the lead of the work is basically how far this particular spiral would travel before it would do one full revolution. And if you calculate pi into that and the angle there, you can work it out. There's mathematical ways of doing it. But this particular book here gives you this rather quickly. Okay, so we'll go over to the back page. And we want to find out what the lead of the work is. That's this chart here. Now, on the left-hand side, we have the diameter of the work. Over here, we have the setting angle in degrees. And here, we have what we call the lead. And they've given an example here. It's written up here. But what we have here is we have a 40 mil diameter. There it is there. We have a 10-degree angle. And all we need to do is put across a rule across there, like this example is here. Put this across here, 40, 10, and then when we see, we have put it right on the 40 onto the 10 there, and you'll see it pretty much comes up to the 700 millimeter lead. It's also in inches as well, and that's given to in inches or metric. We're going to deal with completely metric. Now, if we were changing this, say if it was a 60 mil diameter, we would go 60 with my rule there, 10, and of course this time here the lead would be around about 1,000 millimeters. That's how far it would travel to do one full revolution. So in this case here, we're looking at 700. So next thing we need to look up is what gears will work for that particular example. Now, on a dividing head, it's given, if I can find it. Okay. We'll look at this particular page here. This is a relatively standard dividing head, and we have in our gears, we have two 24s, a 28, 32, 40, 44, 48, 56, 64, 72, 86 and 100. They're the only gears we have. And they're to be mounted up on what we call the banjo, which is in this plate thing that mounts up these gears here. That particular A one there, that is the one that attaches to the lead screw of the table of the machine. Then we have B, which is that's the driver, because this crank handle is going around driving. The B is the driven. That is then keyed to and rotating with C, which is that one there. And then we have an idler here, depending on what's going on here. You may or may not need an idler. And then we have D, the final one here. But the idler is not part of the ratio here. That is just an idler. That does not change the ratio from there to there. That's the driver, that's the driven. The idler, doesn't matter what size that is, the ratio, the true ratio is from there to there. So driver driven, and ignore the idler. Some very cheap dividing head kits don't have actually a 44 tooth. They have everything else but that. And there is always two 24s in the set to make up the 1-to-1 ratio. So you could do a simple 1-to-1 from there to there, 24, 24, and make it up with idlers, and that would be basically tell you the natural lead of the machine. Now, on this particular chart, we look down here, we're looking for whatever the pitch of the lead screw of the x-axis is. And we're working on 5 mil, but this one also works it'll work for a 5 mil pitch lead screw, a 6 mil and an 8 mil, and a 4 threads per inch or 1/4, or a 5 threads per inch one as well. So that will so this particular dividing here will work with any one of those. But in this case here, we're going to work on the 5 millimeter. Now, if I look down the 5 millimeter one, we look at see here these numbers. And now this is the lead, so we're going to look at the 5mm one. So we need to ignore all these here. We're looking down here, and of course these numbers start rising as they come down here. The page is 54. Over to the next one here, up to 93. We're looking for 700. On the 3, 4, 5, 6, where are we? 700, there's 700 there. Now that gives us these A, B, C and D gears. So we need what do we got here? A 24. So there's a 24 on the page. A 24 driver driving a 72. Keyed to a 48. And driving a 56. So there'll be one over the top of that there at 56. So probably rub this one out just so I keep it nice and simple. So that is a A24 driving a 72, keyed to a 48 and driving a 56. And that will do a lead of 700mm. Okay. Now, that's the theory. Things get a little bit crazy sometimes though. We'll give this in a formula. Normally we write this in a fractional form, which is 24 over 72 multiplied by 48 over 56. Now, of course, that's a fraction. They're in fractional sizes, and that's expressing that ratio there in fractional terms. Okay. Now, we may have a problem. On our banjo on the dividing head, going up the side to the input shaft, we may have a problem getting some gears in. Sometimes you have to play around with this. Now we can do a couple of things here. We can put in here, supposing this 24, that's a very small one down here on the shaft, on the lead screw, and there's a 72 there. That's a reasonable size. Sometimes these two gears are quite small. When that happens and there's bigger gears here, we won't have enough room in the banjo to swing that round and engage with the lead screw. So what we do is swap that over. So we put this the other way here, a 48 over a 56 driving a 24 over 72. And you can maybe have a little bit more room there. You have to play around with these things to get them right. Sometimes you can't even get that to work. What you can do sometimes here is, let's give another example. Let's supposing we've got the same thing as before. We have a 24, but we can't reach into 72. We want a bigger one. We do have 100. So if we put 100 in there as an idler, then put the 72 here, we have a 24, idler, 100. This one here, 72, then keyed to a 48, and then to a 56. Now, we've put an idler in there. So what does an idler do? Well, it does two things. It gives us a little bit of space to move around, to engage. But every time you put an idler in, you change the direction. So if you're, in the end, running the wrong helix, going the wrong direction to your dividing head, you'll need to put another idler in here, an idler in there, to make that reverse. So sometimes you have to play around with these things. But that's how you set up the banjo here for cutting, for helical milling. Okay? Now, there's another thing we need to know as well. On the machine itself, let's look at the top of the milling machine. There's your horizontal mill, the head thing over the top there. There's your X table there, and your ways through there, and your dividing head is sitting here, okay, with the tailstock as well, okay, and of course your handle out here with your banjo and the extension shaft out of your dividing head. Now, on a universal milling machine, you can rotate this table. That swings around 45 degrees in both directions. That whole table swings. A bunch of bolts underneath here, and that will swing around. Now I'm going to quote Athol Tonkin, my third year trade teacher for when I was doing fitting and machining. To work out which way you need to swing this table, if you're standing here, that's me, and if you do a right hand push on the right hand side of the table and swing that around in that direction there, that will do a right handed helix because that whole table will swing around there. That will cut a right handed helix with your right hand push here. And if you want to do a left hand helix, you just push the table with your left hand, swing it around the other way, that will cut a left hand helix. And of course, we need to put that in this case here on 10 degrees. So we'll set up our little banjo here for all those gears here on the input shaft there. We will shift this around in that direction there to 10 degrees because it needs to be the same angle as you originally selected. And then you're ready to go. Okay, so that's how you set up a milling machine for helical milling. You can, on a vertical mill, also do helical milling. On a vertical mill, you have a head and a cutter coming down here. There's your cutter. That's your cutter. And of course, this is capable. There's your head of your machine. There's your table. There's your table. And there's your lead screw here. What you can do is put the cutter horizontal, your dividing head over here. You work there. And horizontal there. And what you can do is tilt the head for the lead angle that way and cut on the back of this particular part here, on the back of it horizontally on a stub arbor. And you can also do helical milling without actually rotating a table like a universal mill with that feature that swings, because a vertical mill does not have a table that will swing around. It's not a universal machine. But you can tilt the head to the lead angle one way or the other to allow for to do helical milling on a regular one, on a regular vertical mill, like a Bridgeport or one of their clones. And of course, if it's an aftermarket dividing head, you'll also have to adapt the lead screw out here where the handle goes here. You have to make up a little spacer thing to accept the first gear on the driver, to accept the first gear that engages with the banjo on the back there. And that is how you set up helical milling. If you have a look at my very first video I ever ran called Heilical Milling, have a look at that video there. You'll see this actual mecha dividing head actually being used for cutting a gear. And I'm Mark Wilson, and thanks for watching.